Okay, so I'm going to do a little bit of change to the due date for the project now that you've all started it and I've kind of thought about it. What I'm going to do is I'm going to have it due about 30 minutes or an hour into the next lab, so the Wednesday after spring break. So this way that you have all the spring break to work on it, and then I can actually just check it all off in person for everyone that shows up. I'd rather do it in person than remote. And then if you have any kind of last minute questions, you'll have a little bit of time to work on it then. But you want to get it most of the way working. I will be in my office hours that are immediately after this class. And then if you want office hours over spring break, send me an email and I will try and schedule a Zoom time over meeting. Zoom is really good for this kind of problems, especially, and if you're running into like errors that you can't debug, send me an email with like the code that's having the error, any code that is above it in the hierarchy. So like we're designing the ALU and you were having issue with your adder, send me the adder and the ALU so they can see how they're linked. And then I also need the text from the TCL console. That way I can usually figure out what the error is from those. If you're getting stuck on errors is awful because sometimes they get really cryptic. So I just don't want you to spend 2 or 3 hours on an error that you're just like, I don't know, that maybe I could look out in 3 minutes, you know. Okay, so that's the project. Make sure you don't get stuck on anything. Let's move back to sequential logic. So the sequential logic, right, we talked about flip-flops and latches. The difference being a flip-flop is clocked and a latch is not, right? But both of them function as memory elements, meaning they remember whatever value was put into them, either with a set or reset or a data line. Did we talk about the JK flip-flops? Okay, we'll get to the JK flip-flops then today after I talk about the next subject, which is clock dividers, right? So we've talked about the fact that when I draw a D flip-flop, let's say, and I call it a flip-flop, so that means it's clocked, which means it gets this little triangle flag. And the clock comes in here, right? Okay, so when we ended, we said that the clock has a frequency. The frequency is what the digital logic knows and recognizes as time. So a digital clock looks like a series of 1s and 0 pulses, right? 1 0 1 0. And because there's no inversion bubble on this clock, it means it's rising edge sensitive. Meaning at the rising edge of this clock, when it goes to 0 to 1, it will take whatever is on the D line, the data line, and store it to the queue. And it can't update until the next clock edge. Okay, then I said that there is the relationship here is that, from rising edge to rising edge is capital T, the period, which is then related to the frequency as 1 by f. 1 divided by frequency. They're just opposite, right? They're inverted. So if I have a frequency of 10 kilohertz, hertz has a unit of once per second. So hertz is just saying per second. So 10 kilohertz is saying 10,000 times per second. This clock is going to go. So what is the amount of time between rising edge? Well, it's 1 divided by 10K or 10,000. That is the period or the amount of time. Okay, so a lot of times we're going to have a really fast system clock. So like if we use the FPGA boards that we're going to use in an upcoming lab 7, lab 8, something like that, the onboard clock for that is 100 megahertz. It's very, very fast. But we're going to design a garage door opener. We don't really care if we have a 100 megahertz clock on something that takes 4 seconds to close or 10 seconds to close or open, right? Garage doors are not fast. So 100 megahertz is just ridiculous. So what you may want to do is slow down the clock. So it turns out we can build clock dividers, is what they're called, really easily using DQ flip-flops. And the way we do that is simply taking Q bar, feeding that back around to data, and then Q is now going to be, we'll call it slow clock. So we're putting in fast clock, really, or clock, and we're getting out slow clock. Now, why does this work? Well, first off, I shouldn't have erased my clock. Okay, so if this is clock, let's talk about what Q bar is doing and Q, right? So timing diagrams are usually how we're going to illustrate what's going on with sequential logic. The clocks give us this nice point where we know what happens, right? So the only changes we're going to get are here at the rising edges of this clock. Never else will we change. Now, the exception is, right, if we bring in those delays that I talked about last time, which are things like clock to Q. What is the delay between the rising edge of the clock and when Q updates, right? That's one type of delay that we mentioned. We'll get a little more into details on delay in just a minute, but let's start here. All right, so a rising edge happens, and let's say that Q starts at 0, which means Q bar starts at 1. All right, so then the rising edge of the clock happens. D sees Q bar, right? Because we've created a feedback loop that says Q bar goes back to D. So the input sees Q bar. That means when the clock happens, Q gets what's on Q bar. So it goes to 1. Look at, nothing can change until the next rising edge of the clock. If Q is 1, Q bar is 0 for the same amount of time. A rising edge of the clock happens. And once again, we put whatever is in Q bar onto Q. So they're just going to flip and continue doing so, right? They're going to flip-flop back and forth every time the rising edge of the clock happens. But now what do you notice about the clock generated by Q compared to clock? What's the relative speed of Q, of slow clock? It's half. I have divided my clock speed by 2 with just one flip-flop. So it turns out that it's very easy to create clocks that are multiples of 2 slower. Because we just, if I wanted to divide by 4, let's take another DQ flip-flop. Well, this slow clock is the new clock for that guy. Q bar loops around in feedback. And I'm going to call this Q clock for quarter clock. Right? This divides the clock by 2. This one then divides slow clock by 2. So Q clock is 1/4 the speed of the original clock. When we get to 3610 in the future, we'll kind of investigate ways to generate more complicated schemes of clock division, because there's no good way doing this to divide the clock by 1.5 times, right? That would be really hard. So, but I will cover a way to do that that is pretty easy coming up. So anyways, so if we had a 100 megahertz clock and I was like, well, I really only care about millisecond intervals, right? And say like 100 millisecond resolution is what we call time resolution on my garage door opener, right? Because 100 milliseconds for a garage door opener for humans is fast, right? For computers and digital logic, it's very slow. I would just chain a whole bunch of these to create a very slow clock off of a very fast clock. Okay. JK flip-flops. So a JK flip-flop is going to look like this. And has an associated truth table as follows. We'll call this Q. I don't want to flip. Sometimes I flip J and K, so I want to make sure I don't do that. All right, we're going to actually introduce a little bit of new notation, which this is going to be Qn plus 1, which is to say, what is the next Q going to be based on the J and K inputs, right? So the flip-flop is edge triggered. When the trigger happens, what is the next value depending on J and K? All right. So if it's 0, 0, and this one makes a lot of sense, it's Qn, meaning whatever it was before, keep it. 1, 1 is actually very similar, except for it's not Qn. So that toggles, meaning if it was a 1, it becomes a 0. If it was a 0, it becomes a 1. Now the zeros and ones just act, or sorry, yeah, 0, 1 and 1, 0, the two middle terms act as your set and reset, like we talked with the SR latch, right? So it's really just reset 0, 1. So K is your reset and J is your set.
Say that again, which one is which?
K is reset, meaning K resets to 0, J sets to 1. Okay, so that's your JK flip-flop. Something you'll kind of notice. So there's another kind of flip-flop as well that we really like called the T flip-flop. And all the T flip-flop says is that at the rising edge of a clock, if T is 1, Q flips. It toggles. 1 becomes 0, it becomes 1. If T is 0, then it stays the same. So its truth table is really simple because it has one input, T. The Qn plus 1, meaning the next Q after the clock edge, is just if 0, it's Qn, and if 1, it's Qn plus 1. Oh, sorry, wait, sorry, Q bar. All right, so don't toggle, toggle. That's all the T flip-flop does. What's useful and interesting about this relationship is you'll notice that in the case that J and K are the same, it looks exactly like the toggle flip-flop. So if I have an input that just does this, that connects the J and K so they can't be different, then I've eliminated these two possibilities where they're different, and I result with a T flip-flop. So JK flip-flops make T flip-flops really easy. You just tie the two inputs to the same thing. And I'm gonna steal your side of the whiteboard real quick. Okay, making this is actually trivially easy when you get down to it. So if I wanted to build a JK flip-flop out of a D flip-flop, make sure I do this right. Yeah. Great. So I actually have to say not K. So what this is doing is it's using whatever is stored in those values already in feedback so that they can evaluate. So if I have J and not Q, right? So J not Q, then I get a 1 here. I put a 1 on the D, and on the clock, I clock 1 onto Q. So let's make sure that makes sense. So if Q is 1, meaning, sorry, if Q is 0, meaning Q bar is 1, and J is 1, so J is 1, and we have Q is 0, meaning Qn is 1, 1, 1, we're going to end up clocking in a 1. That's all this is saying. So the feedback is important. I'm going to have you probably do some exercises to kind of work on that JK. I love asking questions that ask about the JK because they have some interesting uses. They're the most versatile of them because they can work as D flip-flops, they can work as Q flip-flops, sorry, as toggle flip-flops. And you can also set them as kind of what we would call the set reset, right? An SR flip-flop. If you exclude the possibility of using J and K are equal, right? So as long as they're never the same, it's an SR. Well, that one is actually really easy to design using a JK flip-flop. Just like that, right? So now J and K are never the same. So I can't have 0, 0 or 1, 1. I'm always setting or resetting. I just built an SR flip-flop out of a JK. We know that a JK flip-flop is really just a D flip-flop with some extra circuitry. We know that a D flip-flop is really just 2 D latches. We know that D latches are really just a modification to the SR latch, right? That was just walking backwards. We started with the SR latch. We turned the SR into a D latch. We turned 2 D latches into a D flip-flop. We turned the D flip-flop into a JK. We turned the JK flip-flop into an SR flip-flop. They all link together. They're all kind of similar circuits. Let's go ahead and build a JK flip-flop in the HDL. So we've started kind of getting used to this process on clock, right? Processes have a begin statement. They don't have a semicolon. And we just need to set up this kind of logic from the JK flip-flop that says if J is equal to 0 and K is equal to 0, then Q is 0. Else if, remembering in VHDL, if you have else if, they drop the second E, so it's else if. J is 1, and K is equal to 0. Then, well, so here's our 0, 0. Here's our 1, 0. So that is set. J is our set. If I had equal to, I'm going to shorthand this next one, 0, 1, then I would have Q get assigned to, well, K is our reset. Sorry, J is set, K is reset, Q is 0. Then I also have, I should add at least this much. J is equal to 1 and K is 1, right? So 0, 0 on the K's, 1, 0, 0, 1, 1, 1 is our last state, and Q gets assigned to not Q. Right, that just.
Shouldn't the first one be Q is equal to Q then?
Oh, yes. All right. Good catch. Yeah. And what's actually interesting is this first line, the way I've written it now, is kind of optional, right? Because if there's no if statement that satisfied 0, 0, then Q would stay equal to Q. We'd be fine. So we could eliminate this one if statement and be okay. Remembering that in this process, wherever I declared the entity, Q could not be an output. It has to be a buffer or in out. Right? Because I can't put an output on the right side of an equation, an assignment statement. T flip-flops are very similar. If you wanted to build one really quick, right? So the two ways that you could build a T flip-flop is I could keep that code that I just erased, and then when I assigned the ports, I would just assign the ports in a configuration that turned it into a T flip-flop. Or I could write a T flip-flop in really just a couple of lines. Oh, I actually forgot one line on the last one, so this is good that I'm going to do this. We need to have that embedded if statement, because I forgot to add if rising edge of clock. Okay, so if rising edge of clock, I forgot that one, right? This is saying that the process executes on clock anytime clock changes. That unfortunately means when it rises or when it falls. All right, so we fix that by adding the if rising edge of clock, or falling edge if you wanted a negative edge triggered clock. And then you have this embedded if statement that says if T, the input toggle, is equal to 1, then Q is equal to not Q. Toggle it. Notice in this one, I didn't use the next if statement, right? I didn't have to say if T equals 0, because if T equals 0, nothing happens. So as long as there's no assignment, nothing happens, we're good. Okay. Next up, we can build what is called a counter out of using T flip-flops. So I've shown you the VHDL for the T flip-flop. So when I draw a T flip-flop, you know what that VHDL is now. So I'm going to build a 3-bit counter. So the first thing I want to point out is if I have 3 bits, column A, B, C, and well, I'm going to not worry about the output just yet. So this isn't the complete truth table. The first bit, it toggles every line, right? And I use this trick to help me draw out binary so I don't have to like count in binary. The second column toggles every 2 times. Or you notice it toggles when I have a falling edge, when I go from 1 to 0 in the previous column. That same thing holds true in the third column. So A to B, A toggles when B goes from 1 to 0. Right? So there's this consistent moment when we change. So if we think back to our clock divider, right? And as long as we're toggling each larger bit column at half the speed of its lesser bit, right? Then we can just count. We build a counter. Okay, so how do we do that? Well, we're toggling, meaning we're flipping bits. So we just want to set up a T flip-flop. That's our easiest one to draw. I'm going to do something interesting here. I'm actually going to share the clock across all 3 T flip-flops. And then what I want to do is I know that there's going to be a condition on Q because we want to know what the output is from the previous one. So here I'm building the output C. That's bit C. Now I'm going to use this label of clock enable, meaning if the clock is on. So the reason I'm calling it a clock enable is because if it's 0, we'll never toggle. We'll never have a change in C. All right, so if it's 1, C will change every time a clock happens, except for we already know, well, I'll get to that in just a second. Okay, and then I also want to feed this clock enable around to the AND gate. So only when clock enable and Q are both true do I toggle what I'm going to call a signal T1. All right, so then if I take the output of this Q and AND it with T1, I'll create a signal T2 at the output of that AND gate. I'm going to call this the second Q B. And finally, I'm going to call my third Q C. Oh, CBA. Yes. A. Yes. Yeah. All right. So now we can do a bit of a timing diagram on this one to make sure that I haven't messed things up, right? So let's assume that A, B, and C all start at 0, 0, 0. I'm going to create a second column that is also ABC, but I'm going to call these the actual ABC, right? So this is what I want. Hopefully this is what we're going to fill in what I actually get. So clock enable is 1. Let's assume it stays 1, because if it's not 1, nothing is going to happen, right? And then Q is just going to change, it's going to toggle every time I get a rising edge of clock. Okay, so I'm going to, I'm going to push you this way a little. Okay, there we go. And we're going to say our clock is this. And I'm going to rewrite that actually. And then we know that events are only going to be triggered on the rising edge because there's no inversion bubble, so just rising edges. So I'm going to add some dashed lines coming down from this at each rising edge because those are my points of interest. Okay, next up, let's go ahead and do Q, or what we're going to actually be C, right? So the first Q is C. And I said C starts at 0, right? A, B, and C, we all want to start at 0. Okay, so then the rising edge of the clock happens and it toggles. It becomes the opposite. And it happens at every rising edge. Okay. Then we know that CE is always 1. So T1, I'm not even going to bother, right? Because T1 is going to be equal to C because clock enable is always 1. That was the assumption I made. All right, now let's look at B. Well, if T1 is now C, right? T1 and C are equal, so I'm not going to write T1. And I have the rising edge of clock. So if I have a rising edge of a clock and C is 1, then I'll toggle. And this is going to be B as a result. I said B starts at 0, right? And now there's a little bit of an issue here. So there's a rising edge of a clock that is kind of at the same time, right? So we have to more or less decide. Let me see what my notes, which way I did it in the notes. Sometimes I like to teach delays before I do this one. Okay. So if I add just a little bit of delay to, well, all of these really. So let's say that it takes just a short amount of time for C to update. Sometimes the ideal situations actually kind of cause a bit of an issue. Okay, so we have a rising edge here. We're not yet 1. C is not yet 1. So that means B stays 0. But now I have a rising edge of a clock and I have C. So with a little bit of delay, it's going to toggle. Here at time, let's see, I'm going to call these times 0, 1, 2, 3, 4. So I don't have to say this in here and everything as much. Okay. So at time 2, the clock is rising edge, but C is not 1. So therefore it doesn't toggle because of the AND gate, it stays. At time 3, we have a rising edge of clock and C is true, therefore with a little bit of delay, it toggles. Okay. So we could go on and do the same thing with A. That is going to be even slower than that because A needs both B to be true and it needs T1, aka C, to be true. So instead of using C and clock, we're using B and C. Right? So, well, and rising edge of a clock. So now we're 0, 0, 0, 0, 4 zeros before we finally toggle. Right? And that's counting. So this is nice because you instead of, sorry, that was really not straight, was it? All right, so this is nice because now we can just count up to a number. And in fact, we can add a little bit of a logic that let's say we want to build a clock divider that is not divided by 2. I want to build a clock divider that is divided by, say, 5. Well, 0, so 1, 2, 3, 4, 5. I'm going to call this the 5th one, essentially, right? Line 5, if I'm not 0 index, 1, 0, 0. And if each of these have a reset added to them, I'm going to erase this. And then I have some logic that takes, well, I want to reset on 1, 0, 0, right? Let's say that I have an active high reset, which is not usual. So we're going to have A is 1, B is 0, C is 0. So that's our min term. Feed those into an AND gate. And then distribute that AND gate to each of the resets. Right, so I'm feeding A, B, and C back around to this AND gate, but have inverters on B and C. Now, whenever I reach 1, 0, 0, I'm going to reset. As soon as I reset, the output of this AND gate goes back to 0. And it will also then have a pulse. So if I'll show you what I mean by a pulse. So the AND gate, because I'm counting to 5, is 0, 0, because this is not true, right? So this is the output of this AND gate. So it just is not true, and it does that 5 times. It then becomes true. And then on the next rising edge has reset things, so it's no longer true, and goes back to 0. So this, then I can use as like a pulse indicator to say, this is 1 clock, 1 rising edge for every 5 counts. Count to 5, reset, count to 5, reset. So this is how I could build a clock divider of 5. Yeah.
Wouldn't you want to reset it on 1, 0, 1, not 1, 0, 0? The 1, 0, 0, that would be the 5th term. Wouldn't you want to reset on the 6th term?
You might be right. I'd have to go back and think about this sometimes because that's, I don't know. I don't usually design them directly this way. There's some VHDL that I'll show you that is actually how we do it. This is kind of the circuit way. You might be right on the 6th term. It kind of depends. A lot of what I would do is for the real, because I don't like the combinational logic necessarily as my output for a clock. So I'll attach it to a DQ flip-flop to make sure I hold on for one whole time, because otherwise it can, if you have an asynchronous reset here, that will cause a problem too. And then the clock will delay by 1, and it should be right, I think.
Oh, okay, then it'll delay the flip-flop.
Yeah. Yeah, so good question. Make sure when you're doing it, because sometimes we'll make assumptions in the digital logic about when to do that reset, and it's common to make that mistake. And it's really hard, because a lot of times your counters will be like 1,000 or 10,000, and you're like, well, should it be 10,000 or 9,999? And looking at a timing diagram to get that kind of 0.01% error accuracy is hard to do. So yeah, beware of your counts. I may have screwed it up. Well, I did screw it up the first time, so don't feel bad if you do. We'll learn it and practice it. Okay. All right, so I've been mentioning these delays. Let's talk about them a little bit more explicitly. So let's say I have some form of combinational logic that feeds into a D flip-flop, and the output of that flip-flop comes back around into that combinational logic, and we have input A. So this is a little bit weird. You kind of saw what happened over here with the timing diagram when I was trying to draw it ideal, because these delays are real and they exist and they kind of make the circuits make sense. So a couple different types of delays and other timing characteristics that we're interested in are as follows. So first off, you have what's called a propagation delay, or something that I'll call lowercase t p, t propagation. That is how long it takes for the gate to react to a changing input. Okay, so if I change, so let's say Q was 1 and A is 0, then this node, I'll call it alpha for now. So Q is 1, A is 0, alpha is 0. 1, then A changes to 1. So then I have a 1, 1. It takes TP, a propagation delay, before alpha updates. So A changes, Q is already 1. Alpha changes after TP, the propagation delay. Now, let's do this. Well, I'll move on to the next one. All right, so that's all propagation delays. The next problem that we have is when we have a clock and let's say this, so this is a clock, and this is our data input. So there are a couple different kinds of delays, and setup and hold time are something we're concerned with. So setup time is the minimum amount of time that you are allowed to, sorry, let me try that again. Setup time is the minimum amount of time that you need to have the inputs stable before the clock. You need to set up your inputs. So here is setup time. Let's say the difference between this third clock and this change in D is 2 nanoseconds. If my setup time is more than 2 nanoseconds, then we're going to have an issue, because the D input isn't going to know whether it's supposed to be a 0 or a 1. Because what's really happening essentially is that it's charging up a capacitor, a device that stores the charge. It knows what the value is, but it takes some time to react to a changed input. If you try and sample or pull in the D, right? So clock D into Q while it's kind of ramping up. So it's going from 0 to 1, and there's this ramp up time, right? It doesn't instantaneously make that jump. That wouldn't make any sense. It does something like this. If it decides that that's its value, what's Q? Is Q 0 or 1? We don't know. So that again enters what we call that metastable position. It's going to decide that it's 0 or 1. We just don't know what that is. That is setup time. The same issue happens on the other side of the clock, and we call that hold time, or TH. You'll occasionally see setup as just TS. I like to do SU, just to be a little more clear. So hold time is the amount of time that you need your inputs to be stable after the rising edge of the clock.
Do that one more time, sorry.
Hold time is the amount of time your inputs need to be stable after the rising edge of the clock.
So just to be clear for the interpreter, the hold time comes at the rising edge and the setup time comes at the falling edge, or both of them?
I will draw a new diagram to help clarify.
Okay.
So a clock is not ideal either. Clocks have some amount of slope on them as well. So data needs to be ready. We'll call from this point the T setup. So your input it can change all at once before here, but then must be stable before that setup time difference of the clock. It needs to hold stable at least until T hold time after the end of that clock. Now, for our purposes in general, we're going to pretend that this clock is near perfect. So that your setup time, again, is just be set. Don't be changing any time between setup time before the clock edge and hold time after the clock edge. So you have this window where you must maintain your inputs at the same value. All right, there is one more, which I instituted over here, actually implemented over here at the A, B, and C, where it is clock to Q. So let's say that D is a 1 and Q was a 0. Well, this clock happens. We're clocking D into Q, right? That doesn't happen instantaneously. It has to propagate through, and eventually it will tick up to 1, right? Because D was 1, so a rising edge of clock clocks D into Q, makes it 1. All right. That delay from the rising edge of the clock to the point where Q changes is called the clock to Q delay. Clock to Q. Occasionally you'll see me write it as C to Q, just to be shorter, clock to Q. So that delay is really important in how the outputs react, right? And it made it a lot easier for me to deal with that timing diagram, because real circuits have delays. Now, there is an issue where this is a very common type of circuit technology, where we're going to remember something and we're going to react both on what we remembered and some input. In order to meet timing requirements, we have to consider setup, hold times, and clock to Q delays. If we don't consider those, we could end up with timing errors and either enter metastable conditions or oscillatory situations, where it's just going back and forth 0 and 1, 0, 1, like as fast as it can. Neither of those are good situations. In both cases, sorry, let me make sure I do it. You can relate the fastest clock speed that you can do, right? Because if this is a really slow clock, like a very, very slow clock, like let's pretend it's like running at once per second, and these delays are nanoseconds, there's just no chance of running into an issue of D not being ready when Q changes, right? In this feedback loop. So what is the minimum time? If it's a really slow clock, we're fine. If it's a fast clock, we can start running into issues. Well, it's a simple equation that just says the period of the clock needs to be greater or equal to, I'm going to just write this out and then I'll explain what it means. Okay, so the period of the clock must be greater than the sum of the maximum clock to Q delay plus the maximum logic delay. So TP is propagation, right? So the logic delay plus the maximum setup time. Now, the reason that I have these maximum words in there are that you can have circuits where the transition from 0 to 1 or 1 to 0 is faster or slower than one another. And so like maybe your setup time when you're going from, actually let's use TP logic. So let's say your AND gate can go from 0 to 1 really fast, but 1 to 0 kind of slow, right? I have to take that 1 to 0 into consideration. And I have to be ready for either case. So I take the longest delay in that. The other one in that logic path is also, what if instead of just an AND gate in this logic, I kind of replace it with just a block. I'm just gonna call that C, where C might be something like this, where there are multiple delay paths. So I might give you a question like this. This asks you, given this circuit, what is the maximum clock speed that you can run at? Given that the AND gates have a 10 nanosecond delay, OR gates have a 7 nanosecond delay, and inverters have a 3 nanosecond delay. Well, what this TP logic max means is I need to find the longest delay. Well, one path, Q2, if I just call this alpha, right, as I did before. So Q to alpha is 17 nanoseconds. A to alpha is also 17 nanoseconds through this AND gate. This path through the inverters looks like probably the longest to me, right? Because it has the most gates. Now, having the most gates doesn't necessarily mean it's going to be the longest, because like OR gates are faster than AND in this case, inverters faster than the others. So if we had like 4 inverters, it has the most gates, but wouldn't be slower than even Q, right? Just a silly example. But here I'd have 3 nanoseconds on the inverter, plus 10 nanoseconds on the AND gate, plus 3 nanoseconds on the second inverter, and 7 on that. So 10, 13, 23 nanoseconds is my longest delay path. All right, so I would add that. So let's say my setup time was 4 nanoseconds. My longest delay path I just said was 23 nanoseconds. And my clock to Q, let's say I defined that as 8 nanoseconds. Then that means my period must be greater than or equal to this sum, which is going to be 27 plus 8 is 35 nanoseconds. How do I find my frequency, my maximum frequency then?
1 over that.
1 over that. F max is 1 divided by 35 nanoseconds. Whatever that is, I don't know. That's how we would calculate that kind of feedback in delays to figure out what our maximum clock speed is. Now, we've got 15 minutes left. I'm going to spend the remainder of those 15 minutes doing timing diagram examples, just so that we get kind of used to writing.
I have a quick question.
Yeah.
How'd you get the 8 nanoseconds again?
I just made up as,
Oh, okay.
I'll give you that value. I'll say like the clock to Q is 8.
Oh, yeah, I thought you.
Yeah, no, yeah, I don't expect you guys to know these because like you would never just like memorize the common delays of technologies. Because in order for you to calculate, I have to be like, given 180 nanometer technology fabricated under these specifications, you know, I would have to give you a page document for you to calculate that.
And also, are there those delays on the gates, are those universal or are they just what you made up?
I made them up. They're all kind of based off of older technologies, actually. These are like
The newer technology probably can go a lot faster.
way faster than that. Yeah, because I mean, if someone wants to punch that in for me, you can tell me what that clock speed is. You don't have a calculator out? That's fine. I can pull up Google here. actually, that's pretty fast. So 1, 2, 3, that's 28.5 megahertz, roughly. Is it maximum clock speed? But I mean, most of you don't remember a time when 28 megahertz was a fast computer, right? 28 megahertz is just not that fast anymore. We have Arduinos that are faster than that for $30 or something. So anyways, that's old technology. Okay. Sorry, did I get your questions?
Yeah.
Okay. I'm sure I have it right. And it doesn't look like I have a document cam in here, which is really unfortunate. So you guys are gonna have to rely on my amazing drawing skills. Let's go with a good one. So this is clock. We're going to have a reset signal. RST is usually what I use for reset. It's going to do. And then data. So we're going to do a D flip-flop. And then we're going to go ahead and say Q. Now, the question would be, given that there is a 4 nanosecond clock to Q delay, draw me Q. Right? Now, there's a couple of things that you want to be aware of. First off, I will usually try and tell you that Q starts at something. If I don't, you could do something like assume 1, right? And just let me know you're making an assumption. Or you can admit that, look, until this first rising edge clock, I just don't know. Unknown, X. Don't know. Okay. Now, I said that the clock to 4 nanoseconds, so then I have to tell you something like, well, the clock period is 16 nanoseconds, so that we have some sense of time scale, right? Okay, so that means that halfway through is 8 nanoseconds, so that means a quarter of the way through is what 4 nanoseconds is. So the clock happens, and then 4 nanoseconds later, that's this point, I can now know what Q is. And Q is just going to be D, except for the fact that I have reset, and I'm going to specify it's an active low reset. So it's busy resetting. Well, what happens when we reset? What does the value go to? 0, right. So I'm going to say, I should have, if I had thought this question out, I would say that it is an active low synchronous reset. Right? Because if it was an asynchronous reset, then we already know it's 0, regardless of the clock. Everyone remember synchronous and asynchronous resets? Okay. So now because I have a rising edge of a clock, active low reset, I get a 0. Now, this is why I go ahead and I mark out interesting points, points of interest, where things might actually change. I know that nothing can happen until this next clock, clock number 2. All right, what happens there? Well, we're no longer resetting and data is high. We go to 1 after 4 nanoseconds. And once again, nothing can change till the next clock plus 4 nanoseconds. Rising edge of clock happens, we're at 0. We drop to 0 there. Fourth clock happens, still not resetting, D is 1. So fourth clock, wait 4 nanoseconds, switch to 1. We'll go until 4 nanoseconds after the, what is this, 5th clock. And then still not resetting, back to 0. Ta-da. So that's the general process that you're going to want to look for, which is identify where it might change, take into account your reset, and then start drawing your D. Okay, I'm going to see. Shoot.
I actually have a question on this last one.
Yeah.
So if at the very last time block, if D was 1, but reset was low, would it have dropped? Would it have changed?
So you want to know this. Right? Something like that.
Yeah.
So D is 1 on the clock. We keep a 1 here instead of dropping to the 0. We can't change until clock number 6. Therefore, we are resetting. And a reset, you already said, goes to 0.
Okay. So if D is 1, but then reset is 0, you would reset at, so like at the next clock point, if it was 1, but you would be resetting, would you still drop to reset even if the data is high?
Yeah, the reset is the most important thing.
Okay.
And reset, unless you say otherwise, reset always means go to 0. And that's just vocabulary, really. It's just definition. It's set, 1, reset, 0. Okay.
And the reason you did the invert reset, right, is so that if that wasn't there, it would reset if it was high.
Yes, exactly. So then we'd be resetting this entire duration except for the very end. So we'd be just zeros most of the way, and it would have been way less interesting. Okay. Let's see if I can draw one more example. If you go on my YouTube channel and go to the, I have a video posted from my night class of this one from earlier this week. That one has a lot more examples. That class is 30 minutes longer than your one because you guys have 2 sections of an hour and 15 minutes, and they have 1 section per week of 3 hours. So I have 30 extra minutes of examples. So if you go kind of near the end, you can see me bungle through some examples that I do terribly and fight with a horrible overhead projector because it's in the other room and it never works. But it does have other examples, and I will assign homework in order to make sure you guys get this. Okay. So sticking to same clock. Reset is going to be low. Okay, I'm gonna add one more condition on this one that says that I want to have a T setup of 4 nanoseconds. So when I do these on like an exam or homework, they're almost always better diagrams than I can possibly handwrite. So first thing that we want to do is go ahead and label the points of interest, right? The rising edges of clocks, so that we have something that might change. Let's say hold time is 0. Let's say it's ideal hold time. Well, let's go ahead and take a peek and identify some spots that might be problematic. Well, here is the most apparent issue, right? That doesn't look like, even in my terrible drawing, like 4 nanoseconds. I don't meet setup time there. All right, well, let's do Q first. I've already labeled the points of interest. On the first clock, we are resetting, so we don't know what it is until, I'm going to erase the clock to Q requirement on this. No C2Q, just setup. Keep this simple. Okay, so I don't know until this first clock, at which point I am reset to 0. Cannot change until the next rising edge of the clock, at which point I'm no longer resetting again. So I go to, what happens?
Sorry, what was the question?
What happens at this clock?
At this clock, on clock's rising up, so, and then resets. It should go to 1, right?
Correct. All right, wait till the next clock. Jason, what happens at this clock?
Am I looking at reset or D data?
Both. You need to take into account both. Because it's a DQ flip-flop.
I'm thinking it's going down to 0 then.
Correct. Yeah, because we're not resetting and D is 0. Great. Now, this one I said no hold times requirement, so that's okay. The D rises here right before the clock. Let's say that is exactly 4 nanoseconds, so we just meet timing. What do we get on Q if this is okay? 0. Clock reset 0. Perfect. Right. Now this one, oh, well, this is kind of an interesting issue. So here we don't meet setup time. What happened? What do you think happens to Q?
That stays at 0.
It might, but we don't know. I mean, it's a good guess, and it probably is what happens. But because we don't meet setup time, we don't know. Because we don't know if reset or D is faster. And since we're not meeting those times, well, D is 1. So if reset is being done, then it's 1. If reset's not done, it's 0. So it could be either one. We don't know. Now, if we had kept D at 0 and you wrote 0, you'd probably be right? Almost certainly. But again, maybe not. So if you don't meet timing, we get don't knows. And in fact, we can't know again until another clock, at which point, what do I get?
No, 1.
Right, so D is 1, not resetting, clock edge, it becomes a 1. Perfect. Okay. That looks like all the time that I have. I'll get assignments posted for this today, actually, so that you can start looking over and practicing these timing diagrams and give me some questions if you run into problems. Don't forget to get your project in mostly working order before the next lab time, that's in 2 weeks, I guess. Other than that, go enjoy your spring break.
The next lab time, are we gonna be working on the next lab, or will that be time to work on our project?
We'll be working on the next lab, but I'm gonna give you 30 minutes to an hour in the beginning so I can go around and sign them off. So you have a little bit of time to polish it, but basically you want to be ready to hand it in. It won't be due that day, so I'm trying to like write up lab report or whatever after that.
Okay.
But I do want to do the sign offs on that day.
Okay, so you're gonna push back the due date on that?
I am gonna push back the due date. Any other questions? Cool. I'll be in my office for office hours for the next hour and a half or so you can stop by and have questions. Yep.